Today, we're going to sharpen our focus on a tool that, might seem simple, but is absolutely critical in any histology lab, the microtome knife. The science behind these cutting edges is really what makes or breaks your ability to get those perfect, super thin tissue sections. So, let's dive right in. This quote just says it all, doesn't it? The entire process of creating usable slides, everything you do for your analysis, depends almost entirely on the quality and condition of your knife. A flawless edge is, well, it's simply non-negotiable. So here's our game plan. We'll start with the history and why that cutting edge is so important. Then we'll break down the two main ways to classify these knives, by the material they're made of and by their profile. We'll explore the common and the more specialized materials. And finally, we'll really dig into the anatomy of the knife edge and see how different shapes are perfect for different jobs. All right, let's kick things off at the very beginning. The search for that perfect cutting edge has been a really long one, evolving from pretty simple tools to the highly specialized instruments that we see facing modern challenges today. So the very first attempt at a microtome knife was, well, it was basically just a sharpened razor blade. The problem, as you can probably guess, is that it got blunt incredibly fast. A huge leap forward came in 1950, when two researchers, Latta and Hartman, discovered that the edge of freshly cut glass was fine enough to produce those high-quality sections needed for microscopy, a real game changer. Now you might be thinking, hey, don't we just use disposable blades for everything now? And look, for a lot of routine tasks, you'd be absolutely right, they're great. But when you're up against tougher tissues like bone, those disposable blades often just don't cut it. So the need for a perfectly maintained, specialized, sharp knife is just as important as it's ever been, especially for the toughest jobs in microtomy. So how do we make sense of all the different knives out there? Well, it really just boils down to two fundamental ways of classifying them, which we're going to get into right now. Every single microtome knife can be categorized in two main ways. First, you've got its material. Think steel, glass, or even diamond. And second, you've got the shape, or what we call the profile of its cutting edge. Understanding both of these is totally key to picking the right tool for whatever you're working on. Okay, let's tackle that first classification, material. We'll start by looking at the types of knives you're most likely to see and use in the lab day to day. So the classic steel knife, as shown here in figure 13, this one's made from really high-quality carbon or tool-grade steel that's rust-resistant and free from impurities. But here's what's really interesting. It's all about how they're hardened. The best knives are what we call fully hardened, meaning they're hardened all the way through. The ones that are only surface hardened, well, they'll lose their cutting edge pretty quickly, as that thin hardened layer just wears away. Now, if you're working with a cryostat, you need something that can handle all that cold and condensation, right? That's where non-corrosive knives come in. They're made from hardened stainless steel that has about 12 to 15% chromium, which gives them the durability they need to stand up to that harsh environment. Next up, we have these super popular disposable blades, which you can see in figure 14. Think of them as refined, thickened razor blades, also made from high-quality stainless steel. Their edges are often coated with platinum or chromium to make them stronger. And for cryostat use, Teflon-coated blades are fantastic because they reduce friction. Plus, their thinner design means they get down to the cryostat's temperature way faster. The one absolute must, though, is that they have to be held in a really rigid holder to stop any vibration while you're cutting. Okay, so we've covered the common workhorses. Now let's move on to the high-performance specialists. These are the knives you bring out when you're dealing with the most demanding materials. Okay, check this out. The tungsten carbide knife, which we can see in figure 15. The numbers on this are just incredible. It's a staggering 100 times harder than tool steel. That gives it excellent wear resistance. I mean, you can get up to 30,000 serial sections of undecalcified bone from just a single sharpening. The trade-off for that extreme hardness, though, is that the knife is pretty brittle, so you have to handle it with care. Next up are glass knives, often called Ralph knives, and you can see their edge in figure 16. Like tungsten carbide, they're hard, but also brittle. Their biggest drawback is shelf life. They literally deteriorate while in storage because of changes in the flow of the glass and also from oxidation. So, the most crucial takeaway here is that glass knives absolutely must be prepared immediately before you use them. The really cool thing about Ralph knives is that you can create different profiles for different jobs. A high profile is perfect for soft media, like waxes. A medium profile can handle both soft and hard plastics. And a low profile is what you want for those hard plastics. There's also something called a front profile, but just don't use it. It's unsuitable because it can create a sloping edge artifact that will completely ruin your sections. All right, now we're at the top of the line, diamond and sapphire knives. Diamond knives are made from flawless, gem-quality diamonds. They are extremely durable, and they're the absolute go-to for cutting very, very thin sections for things like electron microscopy. But, as you can imagine, they are very expensive. Then you have sapphire knives, made from a single solid sapphire crystal. They're actually even harder than tungsten carbide or glass, making them incredibly durable. Their only real restriction is that the knife edge is limited to just 11 millimeters, so the size of your block is definitely a factor. All right, we've covered materials. So now let's switch gears to our second classification system, the actual shape or profile of the cutting edge itself. We'll kick it off with the sharpest profiles. So this right here is profile A, as shown in figure 17. It can be either strongly plano-concave or biconcave. This design makes it extremely sharp, which is perfect for very soft materials like celluloid. But that thinness is also its weakness. If you try to use it on harder materials, the edge is prone to vibrate, which causes that annoying artifact we call chattering. So for the best results, this knife should always be positioned oblique to the block. Next up is profile B, a plano-concave shape. The easiest way to think of it is as a reinforced version of profile A. It has a similar shape, but its back is thicker, giving it more stability. This makes it suitable for materials that are just too hard for a profile A knife, but it's still great for softer things like paraffin wax. And just like profile A, you want to position this knife obliquely to whatever your section. Okay, let's move on to the more rigid and robust profiles. These are the ones designed for the really tough jobs you'll encounter in the lab. Profile C is your classic wedge shape. It's way more rigid than profiles A or B, which lets it cut harder materials like paraffin wax blocks, frozen sections, and even small resin blocks. The trade-off, of course, is that it can't be ground to be quite as sharp. Then you have profile D, the plane or tool edge shape. This is by far the most stable and robust profile of them all, designed for hard and tough materials like those large resin blocks. And, as you'd probably expect, it's the least sharp of the four profiles. So how are these different edges actually formed? Well, the cutting edge is created by grinding a bevel into the steel. For profiles A, B, and C, this means grinding a bevel on each side of the knife to create that sharp meeting point. But profile D is unique. Its cutting edge is formed by grinding a bevel onto just one single angled surface. And that's exactly what gives it that tool edge shape and its incredible stability.